So good morning students. I hope that you all are fine. So till now in the fiber optic communication we studied about the optical amplifiers, the principle and the EDFA, that is erbium doped fiber amplifier. So right now we are moving towards the Raman amplifier. First of all, we understand that what is the Raman scattering. The principle of the Raman scattering is that a lower wavelength pump laser light traveling down an optical fiber along with the signal scatters off atoms in the fiber, loses some energy to the atoms, and then continue its journey with the same wavelength as the signal. So here we can say four things. That first one is the pump wavelength, that is a signal wavelength, and this is a Raman scattering, and this is the signal wavelength after some amplification. Now the Raman amplifiers, it uses stimulated Raman effect and the pump laser whose frequency is equal to the signal frequency plus frequency of a chemical bond in the material. And because it is a non-planar process, requires a very high pump powers in watts. Now the Raman amplification. In this type of amplification, as we can see in the figure, that here is an input signal, then optical fiber, pump laser, output signal, and the pump laser for the counter pumping. The Raman amplification requires no special doping in the optical fiber. It is usually accomplished as the distributed amplification. That is, it happens throughout the length of the actual transmission fiber rather than all in one place in a small box, as in the case with an EDFA. So, if we talk about the Raman amplifier, the Raman amplification uses the common, that is a non-doped fibers working around 1310 and 1550 nanometer. It requires high pump power and the broad gain spectrum. Suppose we have a signal at the 1450 nanometer and the pump amplification at 1453 nanometer. It is an isolator. Here the both signal are combined with the combiner. Now this is a single mode fiber. Here we can see the residual pump energy, and it is an isolator again here, and here we get the amplified signal. Now it is also a diagram of the molecular excitation and new frequency generation. The stimulated Raman scattering is the working principle of the Raman amplifier. The pump radiation excites the molecules to higher energy levels and a new wavelength, that is Stokes wave, in generation upon de-excitation of these molecules. The Stokes wave is having a frequency downshift of 13.2 GHz. This means that if a signal having a frequency shift by 13.2 THz is entering a region having excited molecular levels by a suitable pump wavelength, amplification of the signals occur. This is the basic principle of the Raman amplifier. Now this is a fiber Raman amplifier. It is also a diagram that is an input port. It has a input port and it is an optical fiber. And here is about the backward pumping. Some energy is in the backward side. Then this is a signal or a pump, a combiner, and it is the output port. Here we can see the diagram that this is a pump power, or we can say it as a Raman gain, and this is a WDM bandwidth. So here we can see that this is a Raman gain from here it is increasing, and after that it is steeply decreasing, and this is a pump energy. So the advantages of the Raman amplifiers are: the first one is can use existing fiber as a gain medium, can operate in any region of the spectrum. The multi-pump can be used to generate the broadband gain. Now the disadvantage also there. It requires a high pump power. It cannot be sustained with the low pump power. Second one is the can be used only over the long distances, since Raman effect is very weak. Then the relay scattering dominates here, causing a loss of pump power. Now this is the comparative analysis of the amplifiers, optical amplifiers. That is a semiconductor optical amplifier, that is SOA, EDFA, and the Raman amplifier. The different parameters for the comparison are the gain, wavelength, bandwidth, saturated power maximum value, and polarization, noise figure, pump power, time constant, size, is it switchable or not, then the cost factor. It is an important analysis for the exam purpose. After that, an optical amplifier is characterized by some of the parameters which are the gain, gain efficiency, gain bandwidth, gain saturation, and the noise. As we see, the gain is the ratio of the output power and input power. It is in the dB. Gain efficiency, gain as a function of input power, dB per milliwatt. Again, bandwidth, it is the range of frequencies over which the amplifier is effective, and not much else. Then the gain saturation, the maximum output power beyond which no amplification is reached. After that, the noise, undesired signal due to physical process in the amplifier. After this, again the output versus the wavelength curve. Here we can see that the pump power is so much high here at 1.48 micrometer. Here the window for the Raman is getting about 1.52 to 1.57 micrometer. And first of all, here the gain is increasing, and then decreasing, and then here it is a saturated gain or saturated level. After that, again it is decreasing. So it is all about the Raman scattering or the Raman optical amplifier. After that, we will discuss some numerical problems based on the EDFA and the Raman scattering tomorrow or day after that. So thank you so much.